Welcome to the fastest way to learn data structures and algorithms with this premium revision material. Today we are mastering LeetCode 76, the minimum window substring. This is a legendary hard-level sliding window problem, a favorite in Google and Meta interviews. Let us look at the problem statement. Given two strings, s and t, our goal is to find the shortest substring in s that contains all the characters of t, including duplicates. If no such window exists, we return an empty string. It sounds simple, but the efficiency requirements make it a true test of your sliding window mastery. Think of it like a professional chef searching for specific ingredients in a long pantry aisle. You start walking down the aisle, grabbing items until you have everything on your list. Once you have them all, you try to see if you can discard the items at the beginning of your cart to make it lighter, while still keeping a complete set. If you lose a required ingredient, you keep walking until you find it again. Now, for our strategy. We use the sliding window technique with 2 pointers. By maintaining a frequency count of characters in our current window and comparing it to our target, we avoid redundant checks. The key is the have and need variables, which let us check if a window is valid in O of one time. Let's dive into a step-by-step dry run. String S is our pantry, and T contains the ingredients we need, A, B, and C. We initialize our target counts, we need one of each. Window count starts empty, and our have tracker is at 0. Both pointers start at the beginning. Our moves to index 0, finding A. Since we need an A, we increment its window count. Now we have 1, which matches our target, so our have count increments to 1. Our moves through D and O, they aren't in our target list, so we just keep going. At index 3, we find B. That's another requirement. Window count for B becomes 1, so have increases to 2. We skip E, and hit C at index 5. Now we have A, B, and C. Our have count hits 3, matching our goal. This is our first valid window, a DOBEC with a length of 6. Now the shrink phase. We move L to index 1. But wait, we just lost our only A. The window count for it drops below the target, so F falls back to 2. The window is no longer valid. We must expand R again to find another A. We move through O, D, and E. At index 9, we find B. We already have a B, so while the window count increases, our F count stays at 2. We still need an A. At index 10, we find A. Have is back to 3. Valid window. But it's huge, DOBECODEBA. Let's shrink it. We move L forward, skipping D, O, and B. We can safely lose the first B because we have that extra 1 at index 9. We keep shrinking until L hits index 6. But losing the C at index 5 makes it invalid again. R moves one last time to index 12, finding another C. Now we can shrink L all the way to index 9. Look at the result, B, A, and C. It has all our ingredients and a length of only 4. This is our minimum window. Problem mastered. Now, let us look at the Python code. We start with a quick check. If the target string T is empty, we return an empty string immediately. Next, we build our recipe, a dictionary called count_t to store how many of each character we need. We also initialize a window dictionary to track what is currently in our cart. Here is the magic, we use 2 variables. Have and need. Need is the total number of unique characters in T, and have tracks how many of those requirements we have satisfied. This allows us to check if a window is valid instantly, without rescanning our maps. We use a result variable res and reslen to keep track of the best window we have found, initialized to infinity so the first valid window always updates it. The main loop expands our right pointer R. We grab the character, add it to our window dictionary, and check, do we now have exactly as many of this character as the recipe requires? If yes, we increment have. Once have equals need, we have found a valid window. We enter a while loop to try and shrink it from the left. First, we check if this current window is the shortest we have seen. If it is, we update our result. Then, we try to discard the character at the left pointer L. We subtract its count from the window map. Crucially, if losing this character makes our count drop below the recipe requirement, our window is no longer valid, so we decrement have. Finally, we move the left pointer forward. This constant cycle of expanding and shrinking ensures we find the absolute minimum window in perfect linear time. Looking at the complexity, the time complexity is O of S plus T, where S and T are the lengths of the strings. We visit each character at most twice. The space complexity is O of k, where k is the number of unique characters in the alphabet, since our maps store at most 52 entries.